Welcome back. This is Professor Needing, and this is Math 168. As these things get better in the morning and late at night, I think I should have some outtakes and bloopers. I think they would be kind of hysterical. Took me about 3 times just to get the intro going because just couldn't seem to get the word Math 168 out of my mouth. We're covering Section 2.5, the quantitative variable. We're going to do scatter plots and correlation. Going to want to have your calculator available. And remember, you have to have diagnostics turned on. If you want to know where that's at, once again, second catalog, scroll way down until you find diagnostic on. If you did this at any point in time previously, you don't have to do it again. But if you want to double check it doesn't hurt, hit enter, and hit enter once again, and boom, all done. You probably also want to clear your list in your calculator and make everything go away. And remember, that's a second memory function. So in quantitative data, I remember last time that we were here, we covered categorical. And we did the categorical and the quantitative together, and we did box plots, we did 5-number summaries, and we looked at the spread of data. Now, the visualization for 2 quantitatives will be a scatter plot. And a scatter plot is not the same as a dot plot, 2 completely different graphs. A dot plot is used for a single visualization of a quantitative, but we now have 2 pieces of quantitative variables coming together simultaneously. And the summary statistic will be a correlation coefficient. And that can be in terms of R or in terms of rho, depending on if we are working from a population or from a sample. All these crazy vocabulary words that we use continuously and we rely upon very heavily in order to understand what we're talking about. First of all, a positive association. Remember, this is not correlation. This is not a causal effect or a causation. This is an association. A positive association means that the value of one variable tends to be higher when the value of the other variables are higher. We'll see that in aspect pretty soon. As explanatory increases, the response tends to increase. A negative association between a value of one variable tends to be lower when the value of one variable are higher. As my explanatory increases, my response lowers itself. 2 variables are not associated if knowing the value of one variable does not give you any information on the value of the other, meaning there is no prediction that can happen based on that fact. So what's a scatter plot look like? So a scatter plot is a relationship between 2 quantitative variables, and we have 2 pictures of 2 completely different scatter plots here. You can see that the data is numerical or quantitative on both the x-axis and the y-axis, or the explanatory axis and the response. Remember, the explanatory axis is always on the x if we're looking to make an association between an explanatory and a response. When we talk about cars, for instance, quantitative variables could be weight in pounds, city miles per gallon, or fuel capacity in gallons. These are all quantitative variables that could be measured or surmised about. I want us to make an initial guess or an initial statement about the strength and direction of association. So first of all, when we talk about the strength and direction of association, do we feel it will be a positive association? Do we feel as one increases, the other will increase, or do we feel as one increases, the other will decrease? And do we feel that there's a strong correlation between there? Do you think they're pretty closely related as if they should really determine one another, or probably not? So first one, the weight of a vehicle and its city miles per gallon. Well, my first comment is those 2 things are probably pretty strongly related, meaning if you're driving like me on a full-size 4-door F-150 truck and you are filling that thing with the maximum amount of weight that it can handle, will its miles per gallon in the city change? And the answer is going to be yes. Physics tells us that it takes force to move something, and in order to move something that's fully weighted down, it's going to take more engine, more gas, less city miles per gallon. And that would be based on, again, criteria from the situation. At the same time, do I think this would be an increase or a decrease? Well, I think as the weight of the vehicle increases, that the city miles per gallon will decrease. So I'm thinking we're going to call this a negative correlation or a negative association. Second one, weight and fuel capacity. Okay, so I have this great big truck. I have all this stuff. I want to put more weight in. I want to do things. Should I be able to hold more fuel? Well, I should be able to hold more fuel because I know I'm going to use more fuel. So first of all, I think that this is, again, strong. And why do I think it's strong? Or do I think it's strong in a positive or a negative direction? So what do I think is going to happen to one? As I increase the weight of the vehicle, I believe that the fuel capacity will also increase. Or also at the same time, as you increase the fuel capacity, I believe the weight of the vehicle increases. So again, I think but this one is positive association. Again, thinking in terms of how will one reflect something changing on the other. And here's a couple of graphs. And notice that in these graphs, one is between weight and city miles per gallon, and one is between weight and fuel capacity. So let's look at the left one first. As city miles per gallon increase, the weight comes down. So that would be accurate. You're getting better miles per gallon. You must not be driving a vehicle that weighs as much because mass, force, inertia, all those items. Fuel capacity. As you increase the fuel capacity of a vehicle, well, then the weight of that vehicle is getting heavier and heavier and heavier. We don't need a 40-gallon fuel tank in a Prius. But yet at the same time, in a large truck, in a large van, in a large vehicle, you need a larger fuel tank or the customer is not going to be happy stopping every half of an hour for gas. A summary statistic for two quantitative variables. We use the correlation coefficient. The correlation coefficient, or referred to as just simply the correlation, is the measure of strength. I do a little highlighting here because that's important. It's the measure of strength and it's a measure of direction of a linear association. Linear meaning straight line. Strength meaning how strong, weak, okay, very strong, no strength at all. And what direction, positive or negative. The sample set correlation is R, and the population correlation is a rho. They mean the same thing, but they're for two completely different sets. Between a positive and negative association. In each case, do you expect positive or negative association between the two variables and why? Okay, so let's actually do a little measurement, if you will, here between these two. So the number of years of education and annual salary. So what I'm saying is if I go to college for a bunch of years or even any kind of school, do I expect my salary to change? Most people would tell you, heck yes, because that's the reason I'm going to school, so that I can make more money. So when I look at something like that, I have to say, okay, fine, a couple of things. First of all, do I think it will be a positive or a negative correlation? I think it will be, first of all, I think it will be a positive because I think as my number of years of education increase, my annual salary should increase. So it's a positive correlation. Size of the house and the cost to heat that house. Okay, so think in terms of if your house is larger, should it cost more money to heat that house? And the answer should be, yeah, it should. Will it always? No. Could be sitting in a tropical zone to where it doesn't matter. Heat doesn't matter. But if we're measuring house and what it takes to physically heat that house, more square footage, more cubic feet is going to require more heat process. So, yes, it's going to be, again, a positive correlation. The number of text messages sent on a cell phone and the number of text messages received on a cell phone. If you never send a text message, you probably won't get very many text messages. You'll get some, you'll get spammed, but if you are sending text message after text message after text message, you're probably going to receive a lot of text messages. So there should be a positive correlation between these two. The outside temperature and the amount of clothes worn. Okay, well, this could be read in a couple of different ways. First of all, what do you think would happen if the temperature goes up? Well, as the temperature goes up, the amount of clothing worn should go down. What do you think as the temperature decreases? Well, I think that the amount of clothing worn goes up. So those two things are acting oppositely. So because they're acting oppositively, it'll be a negative correlation. 1 second, I have to put a battery. Sorry about that. I had to change out the battery on my microphone. So anytime they're acting opposite of each other, it's a negative correlation. So what is this correlation number? Well, first of all, the correlation number only exists between -1 and +1. It exists nowhere else. If I tell you that the correlation is -1.2, I'm lying. It can't be -1.2. If I tell you it's 3.4, again, not telling the truth, it can't be 3.4. It's anything from a -1 to a +1 and any decimal in between, including 0. The sign indicates the direction of the association. So if I give you a R value, which is greater than 0, it's a positive association. If I give you a correlation value, which is less than 0, it's a negative association. And if I give you an R value that's close to 0, notice that a little approximation sign says close to 0. Doesn't have to be dead on 0. There's no linear association. The closer we are to 0, the lesser we have of any type of correlation or any kind of association. It says the closer R is to positive and -1, the stronger the linear association. I'm going to jump outside into Stat Key here real fast. I'm going to go into some quantitative data. 1 quantitative, 2 quantitative, right there we go. Here goes some data values right here. And let me see if I can find something a little bit better. Let me go down through. Let me find, this one. So let's say this right here forms a beautiful kind of straight line if I look at it. First thing I want you to look at is over here, the correlation R value, 991. That's super close to +1. And look, if I show a regression line, look how close all the dots are to that line. Now let me go find something, maybe if I can find something that's not quite so nice. See how the dots are a little bit spread out? Look how the correlation came down, 863. Let me find another one. Look at that. Came down to 0.8, so it's coming down. How come it's coming down? Because the dots are spreading themselves out from the data a little bit. It's still good, though. Restaurant tip. There goes a 0.915. That one's pretty good. Hot dog. I don't know what that one is, but I'm going to check it out. Oh, hot dog is only 0.72. It's getting weaker. As the number comes closer to 0, the association is becoming weaker. I want to find a negative one for you. Nope. Sorry, I should know a negative one in here, but I don't know a negative one. I'm just kind of rifling through them. Oh, here, maybe this one. No. Boom. I'm going to have to find a negative one for you somewhere to where one comes down. But what will happen is the line itself will go downward. Boom, I got one. Negative going downward, negative 0.5057. But yet at the same time, two things I want to read here. One, it's going downward, so it's a negative association, but it's a super weak association. It's so close to 0 that I'm going to tell you it really doesn't exist. Heart rate and whatever this is here really don't have much to do with each other in this data plot. Even if I switch the variables, it still stays the same. Notice that switching the variables does not change the R value of the correlation. So again, look how spread out all the dots are. Weak, 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 because of the small correlation or the close to zero correlation. R has no units and does not depend on the units of measurement. The correlation between X and Y is the same as the correlation between Y and X. You just saw me do that when I flipped them. Which of the following scatter plots would below does the correlation of R 0.09 match? Okay, students have an incredibly hard time with these, and I'm going to try and do as my best I can with you. So first of all, the R value here is positive. So when we're talking about a positive R value, this trend line has to go in an upward direction. Okay, has to. First of all, this trend line is going downward here. This trend line here is going downward here. This trend line is going upward, and the dots are pretty good. This one, I'm having a hard time with it, but maybe that's it right there. Now, this is a terrible R value, which means the dots will not be close to the picture. And they have to kind of go in an upward pattern. C is going to be my best choice here. Why not D? Because D is too good. Why not B? Because it's going downhill. Why not A? Because it kind of also looks like it's going downhill. I have a really hard time between choosing A and choosing C, but I can choose C over A. With which of the following scatter plots does the criteria below follow? So now look at what we have. We have a negative correlation. So we want to find dots that are negative going downhill. This one is a no. These are going uphill. Now this one is a negative, but those numbers are pretty darn good right there, right? And this is that same charts. This is that downhill one. And remember, this is that funky uphill one right here. And that one was kind of the same way. So now I want of the two negatives, which one is not as good? This one would be much better than a 0.3. This would be like a 0.7, a 0.8. If you spend a little time rifling through these over here and looking at the R value and looking at the pictures, you can get a pretty good idea of what happens to the dots and how things change. Look how close all those dots are, 0.993. As those dots move their way, look at that one, 0.994. As they move away, then they become not so nice. Look at these. These moved out a little bit, 0.662. So being at a 0.05 is a terrible, terrible statistic. So anyway, back to this one. The one that I'm picking is letter A because A is not very good. Correlation cautions. Correlations can be heavily affected by outliers. Always plot your data. R of 0 means no linear association, and the variables could be otherwise associated. Always plot your data. And correlation never implies causation. If we look at these two pictures, they give us the R values. Notice that the R value of the left-hand side is 0.43 in a positive nature. I know it's difficult, but there's a dot here and there's a dot here, and they kind of go up. They are difficult at best. This one is so random and so scattered that I'm not quite sure I could even tell you exactly which way it goes. And look how close it is to 0. Now here goes one that we've seen before. And we talked about this early in chapters, and I said, hey, we're going to come back and talk about this R 0.74 thing later. So this is the one where we talk about owning TVs and life expectancy. And remember, we debunked this, that there was a confounding variable, and that confounding variable is wealth. But there's still an association. We can't ignore that fact. When the data is put into a computer, or the data is calculated by hand, it has an R value of 0.74, which is not too terribly bad. It clearly shows that there is some kind of association between owning a lot of TVs and life expectancy. But we know from past work that that confounding variable, or that added piece of data that's helping drive this line, is the wealth of the person owning the television sets. Go grab your calculator, and we are going to input this data into our calculator. We could use StatKey, but I think it's better if you use calculator, since that's probably what you'll use on a test. We're going to go into our calculator, and we're going to put this in for list 1, and we're going to put this in for list number 2. Take a second, grab your calc, come back, I'll restart the video, and we'll continue on. Okay, so what we're looking here is a correlation coefficient. So if you take that data that you see on the screen, and you go to your calculator, and you go to Stat, and you go to Edit, and you enter those data into L1 and into L2. Okay, so make sure you have the same count X and Y. The L is the X, and the Y is the L2 is the Y. X, comma Y, L1, comma L2. Now what we're going to want to do is, since we want a correlation coefficient for this, we're going to go to Stat. We're going to scoot over. 1 second, please. We're going to scoot over, and we're going to go down to ABX, number 8. My computer is really slow. Now, we have to make sure that our X list and our Y list is appropriate. Remember what we put in X list? We put in there, and I'm going to change this to L1, and my Y list is in L2. Okay, you got to be careful if you have multiple lists. We're going to run down to where it says calculate. We don't need to worry about frequency or stored regression equation. I'm going to run the list, and I am going to get the bottom calculation, which is called an R value. The R value for this data is 0.927. So we go back to our work. The R correlation to 3 decimals is R point, I already forgot what it was, 0.927. That is how you run an R correlation from a set of data. Now, I suppose I'll show you one other thing while we're here. Remember previously I showed you how to run a box plot and how to put a box plot on your graph. Well, we can also, instead of running a box plot, we can graph this statistical data that we have sitting right here. So if I want to graph these as dots onto my calculator, so remember where we got the stat plot at? We went second, and we went to y equal. I still have my box plot turned on from previously. So if I go into there, remember, you should always turn these things off when you're done with them. I'm going to go down, and I'm going to change from the box plot to the scatter plot. The scatter plot is the first one. Hit enter. It automatically pops up. It says L1 and L2. If it isn't L1 and L2, you need to change those appropriately. And I'm going to do the same thing again. Zoom 9, same as the box plot. Here are the dots for the scatter plot. When we start making the correlation equation, I'll show you how to put the correlation equation up through the dots and see how the best fit is. But that would be a little premature at the moment. Question number 18. Let's take a look at question number 18 here. It says, it is hypothesized that humans originated from East Africa and migrated from there. We compute a measure of genetic diversity for different populations and the geographic distance in each population from East Africa. As one would travel over the surface of Earth by land, the relationship between the two variables is known below, and the data sets are given as genetic diversity. Okay, so we need to make a mental note that genetic diversity is the data set that we're talking about, and that is referring to StatKey. Describe the relationship between genetic diversity and distance from East Africa. Does there appear to be an association? If so, is it positive, is it negative, is it strong, is it weak, is it linear, is it nonlinear? Well, first of all, I want to go to StatKey. I want to make this happen. So let's go to StatKey. Now, the first thing that's going to happen is you're actually going to have to go to data sets, and you're going to have to get this genetic diversity. Upload or unlocking power of data sets. We need to scroll down and find genetic diversity. It's right here. It's under football brain. Click on the CSV. It'll download into your folder wherever your downloads go to. I can't tell you where that happens at. Come back to stat key. Remember what we're working with. We're working with two quantitative numbers. So you need to click on the two quantitative selection. Once we're in two quantitative, we're going to upload that data set. Upload. We're going to go to downloads. And from downloads, we're going to choose genetic diversity. So we grab that. Now remember what it said? It talked about the distance away from. So I'm going to click on the distance value. So I need distance from East Africa first, and I need genetic diversity second, because that's what it said. We're using distance X, the explanatory, to predict genetic diversity Y response. If you mess those up, you can re-click them, but it tells you right up here, X and Y, and it color codes them for you. Here's the genetic diversity stuff. First thing I want you to pay attention to is the correlation, 0.835. Not too bad at all. It's a negative correlation. As the distance gets greater, evidently the genetic diversity gets smaller. 8.35 says it's pretty strong, and if I show a regression line right here, I can kind of see that trending line coming down through there. It's not a bad idea to sit here and guess and go, where would I put the line at, and how close was I? Going to jump back over to the questions here. So the questions were, describe the relationship between genetic diversity from the distance from East Africa. Okay, so my description would be, as the distance increases from East Africa, one's genetic diversity lowers, or trend is to be lower. That would be one. The second thing I would talk about is there's a negative correlation of 0.835, suggesting the association is a strong negative correlation. That would be considered strong. Anything above 0.75 is strong enough to talk about. What else was there? Strong. And is it linear or nonlinear? It is definitely a linear association because it forms a linear trend. If it was a U shape or an S shape or some other shape, then we'd have a different discussion. But in this class, everything's linear based. The correlation is, and here are the choices. Well, go back to where you just ran it from, and it's 0.835 negative, and it's 0.83 right there. And remember, it's negative 0.83, not positive 0.83. And we could kind of pick that out from here. For instance, how could I pick it out if I didn't have stat key? This one is ridiculous. It's too big. This one's ridiculous. It's too big. There's no way it's positive because it doesn't go uphill. So everything I'm slashing out can't happen. This is horrible. You couldn't even tell. It would be nothing but dots just everywhere. On which continent is the population with the lowest genetic diversity? On which continent is the population with the furthest from that? Well, there's two ways for you to get those answers. One, if you can go in here, here's this one here. So you kind of got to hover over this, and you got to look at this number. So when it has an X value of 24198, that's my highest. The one over here with the highest appears to be this one at a 2465. So what I can do is I can go into edit the data from here, and I could look, but you can see it's nothing but numbers in here. That's not going to do you a lot of good, right? Remember, though, I have that genetic diversity CSV. If I open that genetic diversity CSV up, and you don't have to have Excel to open, you can open with many other things also, including Google Sheets. If I find that number in distance here from this column, I'll have the associated country over here. So I'll let you pull down through there and go find that. We don't need to sit here and scroll, but what was that first number? That number I was looking for was 24,198. So if I went in here and let's say I'm going to sort this bad boy, I'm going to do a little sorting here and filters, 24, and I'm going to sort from largest to smallest. There it is, 24,198 right there. And I get this country in Brazil. And if I did it the other way, to remember I wanted the highest genetic diversity. So if I went from there, I could look at that, or I could look at the genetic diversity in the other direction. Okay, so being able to open that file saves you a little bit of time and be able to do that. If not, you could just pick through it and you can still find it. I'm just using some skill from Excel. And lastly, this chart of visualization and variables and summary statistics is a phenomenal chart to have on hand. I posted this for you in Canvas, and it's underneath of announcements. And it shows that if we use one categorical, we'll be using a bar chart or a pie chart. And this is our summary statistic: frequency tables, relative frequency, and proportions. If we're using a single quantitative, it's a dot plot, a histogram, or a box plot. And all of these values are statistics that we can utilize for one quantitative. If it's a categorical versus a categorical, remember this is a stacked or segmented bar chart. Two-way tables and differences in proportions. Has to be differences because now there's two categories. Quantitative and categorical, this is all box plot stuff. And we use difference in means because that's what quantitative values use, or means. And lastly, now we have covered the quantitative and the quantitative, which is always the scatter plot and always the correlation factor. When we come back, we'll be wrapping it up closely for chapter 2, and we'll be moving into linear regression and working with more scatter plots and more correlation coefficients. I'll see you then. Have a wonderful time